Okay, we have a kind of a fun series problem today. We've got the sum from n equals 1 to infinity of 1 over n times this nested radical of n square root of n onto infinity. So to get started with it, the first thing I really need to deal with is this nested radical situation. It's kind of hard to deal with in this form right here. Well, what I can do is I can kind of change the way we write this and kind of break it up. We're going to have, no matter what, this is just an n here. So we have an n out front. For everything else, a square, let's change the notation and write this like we have all this stuff. Instead of writing the square root, let's write it to the half power. And so then we'll have an n here, and this one's just inside of one radical. Then the next one, same kind of thing. The inner part is really the same as the outer part. So instead of writing it with that square root notation, let's do this. Let's write it as n, and then create another 1/2 here. And actually, let's get rid of the dots because they're not, all these other terms are going to be within multiple radicals. So we kind of want our dots embedded. And then this is going to repeat again with another 1/2, and this is just going to keep going like this forever. And then from here, what we can do is we can kind of distribute in these exponents. So the first n is just an n. This second n is just under one radical, so I can write this as n to the 1/2. The third one is under this radical and this radical. So if you multiply this times this onto this becomes n to the 1/4. This one is under 3 radicals, so it's n to the 1/8. The next one's going to become n to the 1/16, n over 132, and this is just going to go on forever like this. But now that we have it written all multiplied out like this, we can see that on everything we just have the same base, different exponents, but we know exactly what that pattern is because it's like 1/2 to the 0, 1/2 to the 1. This we could look at as 1/2 squared, 2 cubed, 2 to the 4th, 2 to the 5th, etc. And so when we multiply these all together, all we're going to do is add exponents. So what we end up with in the exponent is this giant exponent, 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16. You get the idea. This will go on for the rest of your life. Well, putting aside the base for a second, let's just figure out what this giant exponent is. You may already know what this is. You may notice that it's a geometric series. If you just take the common ratio, if you multiply to get to any term, if you multiply by 1/2, 1/2 times 1/2 is 1/4, or like 4th times 1/2 is 1/8, 16th times 1/2 is 1/32. So what we can do is put it in the sum notation. We have a geometric series from 0 to infinity, and we can just write it as 1/2 to the n. Noticing you plug a 0 in, you get 1, you plug a 1 in, you get a 1/2, you plug 2 in, you get a 4th, etc. But for the geometric series, we've got a formula for this. We can write this as 1 over 1 minus the input, which is just 1/2. Reduce the fraction on this, the denominator is 1/2, flip it, and we've got a 2. So it turns out that this whole exponent right here, this whole thing is just equal to 2, and then therefore this whole denominator is n squared. So what we're really looking at is something a lot simpler. We're just looking at the sum from 1 to infinity of 1 over n squared. Looking at it this way, if you had any questions about the convergence initially, now it's clear because on this, you can just use p-series on this. The p-series tells us if we've got a sum like this, 1 over n to some power, if p is greater than 1, then this converges. So we know it converges, but what value is this thing going to converge to? Well, I won't work out the details right now, but this is a really well-known value. This, for one thing, this is the same thing as the Riemann zeta function at 2, but it's also the Basel problem, and we've got a well-known value for this, just pi squared over 6. Okay, that's it for today. Thanks everyone for watching. Have a good day.